To be frank, we will not be on the exam. So if you want to kind of phase out and not listen to anything here, it's fine. I'm going to talk about more advanced techniques or like new and popular topics in our computer architecture that are not essentially related to some of the traditional architecture that we've seen. For example, the traditional architecture are things like you have the CPU, you have the memory hierarchy, and you want to look up the data. You go to DRAM, you get that data back, right? Today we'll talk about, okay, what are other things that can be done through the hardware. I'm not saying, hey, this is our task to come up with all these things, these new hardware design, but it's more like, hey, if you think about it, everything you develop are tools, right? At the end of the day, you are building tools for any user from the software, right? Anyone who uses the software should feel like, hey, this is good, this is fast, this is convenient. Which means that you can change the software, you can come up with new software, you can change the compiler, you can change the OS, you can change the system, you can change the algorithm, which also include you can change the hardware. Everything we do as an engineer or computer scientist, we do for the future. We do to develop tools for other areas of science, right? For them to pick it up and use it. So the first topic that we talk about, we covered this a little bit at the end of the GPU lecture, if I recall correctly, because it is called systolic arrays. And it basically rethink how you consume the data. Fundamentally, when you have an operation, they produce new data, right? So you took OPL before, everything in functional programming, you have a function, you have inputs, it produces an output. If you haven't checked OPL, or if you are still taking functional programming, or you never take that class, basically, you can write a computer program as math function. When you have a math function, what do you do? What do you typically have? Have inputs, have the function, and you have the output. The output is some mathematical operation done on the function, which means that once you have a data, you put that as an input, put it through the function, you get a new piece of data. This new data is consumed by future operation, right? Direct acyclic graph again. This concept of having graph and having direct acyclic graph is everywhere. Actually, a lot of things you learn in algorithm and theory and data structure will appear everywhere from this point on, right? Your life will be revolving around these concepts. If you hate this kind of concept, maybe it's time to make sure you don't hate it at least. Sometimes we call this a producer-consumer model. You have a producer that produces something where you give that something to the consumer. Consumer say, hey, I got a new object. I'm going to take it and I am going to consume it. Question that we can ask in the hardware. By the way, if you have any questions at all about today's lecture, feel free to let me know. These are really pretty much open-end discussion. It's a lot of like design stuff that help certain tasks. And it's still pretty open-end. There's no strict, hey, you have to design it this way or that way. There's no strict science yet, right? There's measurement, there's trade-off. The trade-off can be more performance, a little bit easier to design, or more energy efficient. But the question of a systolic array, do we always need to fetch and decode? Right? From the GPU lecture, we already understand that, hey, if I need to do 32 add or 32 multiply, I can have one fetch and one decode because I know exactly what I'm doing, right? So the purpose of fetch and decode are basically to understand what is the instruction so that you perform the correct task, right? So fundamentally, the decoder is needed because you need to figure out what's the next instruction supposed to do. But what if we know? What if we say, hey, I know exactly what I need to do for the next operation? What if I know exactly, hey, I'm going to do matrix multiply, I need to do convolution, I need to do things like list square fitting, right, on certain amount of input. These days, you can even think about what if I want to do a layer of deep learning. I want to pass I have my input data, I have a layer in deep learning. I want the output. You know that model, so you actually can have the model in hardware. You don't even have to fetch and decode, right? What if you know many upcoming instructions? You know exactly if you see this instruction, it means that it's going to add, then multiply. What if the upcoming instructions always follow the same set of operations? Then we need a super predictable set of operations. Do we need fetch and decode now? The answer is not really, right? If you know certain set of instruction comes in a series, why don't we just combine all of them? And you can actually do that. You can actually build a series of compute units to process multiple operations together. The question is, well, if that's the case, why can't we daisy chain these processing elements, right? And carefully orchestrate how you control the data that flows around the processing element. And that's the idea behind Systolic array. So you might have seen this slide before. Basically, instead of having fetch, oops, always forgot to use a pen. So fetch, decode, do something with that, write it back to memory. You know exactly that you have to go through multiple processing elements, so you can daisy chain them, right? And get this multiple processing elements done one after another. So here's the basic idea. You have a data that flows through multiple processing elements before the results are written back to the main memory. What is the upside of that? Basically, you need to write to the main memory to make it committed to the architectural state. Someone see the results, right? That's when you need to write back to the main memory. So this is the concept behind a lot of this special purpose accelerators. What does it mean? It's a small, simple, regular design that have a lot of concurrency. You can keep the data flowing through multiple stages of the processing elements. EE is processing elements. And this helps balance how your algorithm from the software demand different amount of the compute unit. Compute unit, which is the CPU, processing elements, the ALU, and the memory bandwidth, right? How much memory do I have to bring in to the processor? If you don't have to bring into the processor, you can skip. Didn't we just pipe? This sounds like pipelining, right? You do fetch, decode, execute, memory, and write back. You forward the results to the next stage. So in systolic array, structure can be nonlinear and multidimensional. So think about it, instead of having one pipe in a pipeline way, you now have a series of pipes going around your design, right? The connection between each processing element can be multi-directional. You can have local memory, you can have register, flip-flop. Anyone ever hear about the word flip-flops? Yes, no, flip-flops. Okay, so you might have recalled something like this. If you said think so, in, flop, reset, out, and then the negate version of out. So basically, what is flip-flop? It's something that you need to something that can store your data, but it's really fast. It's really fast. You can store new data every single cycle, as opposed to the memory where you need 50 of cycles for storage. Downside of flip-flops is much bigger than SRAM, right? So these are basically logic that you can use to, instead of doing add, multiply, now you need to store data. You allow them to store the bits, ones and zero, and you can use it in the next cycle, right? So these are flip-flops. Is for trade-off is really fast. You can easily implement them in the logic layer. Logic layer is where your processes is located, right? And you execute what we call kernel. I kind of love to call it compute kernel, just so that I don't confuse it with the OS kernel, right? But it's basically, when you say kernel, it's a core of your code. So the reason why I personally call this compute kernel is because it's a code that will do some series of computation. It's not a defined thing. So people still use the word kernel to refer to this block of computation. Example here, you can use multiply add for matrix multiply, which means you can use it for deep learning. Right over here is the series of overlapping operations. You have x, w, and y, right? And you can do a matrix multiply by decision this multiplier, right? And then add it together. So these becomes the result. So this is kind of like the results that you aggregate. This is the input. This is the input. And you basically can first multiply x and w, put it through the adder. Latch is flip-flops. The difference between latch and flip-flop is that latch is smaller, but it's a little bit weaker than what flip-flops can do. In this case, you can still use a latch. Latch means that I'm going to delay that signal for one more cycle. It allows you to delay the signal. Flip-flop allow you to actually store it for multiple cycles. Latch will just delay it for one cycle. So it basically means you have input coming in, you store that signal x1, for example, x1 over here, so that you can use it to multiply with w1, store them for one cycle before you add it later, right? So when you have this series of latches, it means that you need to time it perfectly. You want to make sure that x1 is getting multiplied with w1. This is correct. You want to make sure that this never happen. You have x1 coming in and it accidentally get multiplied with w2. That's not the correct way to do matrix multiply. So basically in Systolic array, the complicated part is how to orchestrate all the inputs so that you get the correct output. Why is it hard? If you look at matrix multiply or multiply as not as bad yet. But let's say I want to do least square fitting. Here is the design. And if you want to dive into the detail of least square fitting, please go check the paper that I said earlier. So this is the copy of the diagram from figure in the paper that I said earlier from H.C. Kung. Sorry, I might have mispronounced murder his last name. Sorry. But basically you will then need to figure out, okay, for each of the X components and the Y components, right over here, how would you time it such that you can perform least square fitting? Each of these boxes are different type of elements. Each of the circle is different type of elements. I actually forgot what they are. So that's why if you're interested, please check it out. I'm not sure is it like add, multiply, or is it like actually do more than just add and multiply. The point over here, the point of this is you see that this is the series of data input. You time it such that they go through your processing elements and you get the output back. That is the correct version of your function. This function, least square fitting, is pretty complicated, right, to do in software. Well, you can do that in hardware. So now that you see some of the example, you might have been wondering, like, oh, these things seem to be super complex. How can I come up with one, right? So the complexity of the design is actually increasing with the dimension. For example, with the least square fitting is really oddly like organized. Each of the processing elements can also have different amount of time it takes to process the data. As we discussed earlier, adding is is faster than multiplying. So if you have a multiplier followed by an adder, you need to time it perfectly, right? So you need to actually figure out when the data will be produced and time it correctly as the input to the next elements. So that's one of the complicated stuff. The second consideration is if your program demand more processor, demand more compute power, usually you say, okay, you have the code running on the GPU and it's not powerful enough. You need more parallelism, for example. You need more memory bandwidth, for example. What you have to do to design a good systolic array is you need to pinpoint the bottleneck of your application. How do you do this? Typically, you will first need to analyze the actual algorithm down to simple maths and see how common are each of the mathematical operation and where is the dependency. Then look at the data dependency. After you have this, it actually will come a lot more clear on, okay, we have data dependency this way, these data have to wait for this data, this becomes the input to that function. The systolic array design will come based on this analysis. Any questions so far? And I'm not going to ask you to implement any of this. Basically, these are like, okay, if you're curious about neural network accelerators, these are some of the things that can be designed. So the pros and cons. First of all, you minimize data transfer, which is typically a killer for it kills performance. Right? It takes time and consume energy, and it can be really fast. Downside can be pretty hard to design. It is very specialized. You need to define a different symbolic array for different type of application. And your application has to be pretty regular. It is not as flexible as a typical hardware or the CPU or GPU. When I said not flexible, I would like to define what is general purpose processor versus accelerators. General purpose processor is what you learn in this class. The CPU, the GPU, things that you can program, things that can run all program well to some extent. Right? Accelerator, as the name suggests, is designed to accelerate certain tasks. So it's designed to run only subset of things. And it can provide really high performance, so it can be really fast. The design, as I said, it depends on the task you want to accelerate. Typically, you need to address the bottleneck of the task you fix. In general purpose processors, for example, if you run something on the CPU and say, hey, my program can use thousands of threads, right? I would like to use thousands of threads. CPU only contains 8 threads, so it would perform poorly on the CPU. What's the obvious second step that I would do? And this is actually true. So let me tell you a story, right? I might have told you about the paper about that perform DNA sequencing. It's like a hardware design just to do sequence alignment, which is a part of DNA sequencing pipeline. The way we figure out, hey, we need to design a special type of hardware is because we first do this on the CPU and then figure out, hey, the CPU is not giving us enough parallelism. I can use a lot more threads than this. So we are like, okay, let's use the GPU. That's the obvious next step, right? So we run this on a GPU and say, hey, performance is not that great yet. We don't see the expected speed up that we are expecting to see. It turns out the workload has tons of shared data. Why they have tons of shared data? Well, they not tons of shared data, but it demands a lot of cache. They demand a lot of cache because the DNA sequence that is called a read. A read is basically a fraction of your whole genome. The whole genome is those ACTG string together for your for one, I guess, for a human being, right? Read is a subset of that. It's still too big to cache in a GPU cache. So every time you want to access the data, you go to DRAM. What happened next? DRAM doesn't have enough bandwidth. And it turns out there's a whole dependency involved. So we figured out, okay, let's actually design a hardware to do this task, which is essentially string matching. It's an approximate version of string matching. That's how we can identify that, okay, we really need to assign and come up with accelerators. Typical design process, first of all, you need to understand the underlying algorithm, what's the math behind it, and measure and analyze performance on certain general purpose processor to see how data is being consumed. So you know this function produces data for the next function. This function becomes the time consuming part because it requires a lot of bandwidth, a lot of CPU power. And then you start from scratch. Look at the algorithm again and only add component just to satisfy the computation for the function that you need and minimize data transfer, data access between the processing elements and memory. And that's it. Basically, it's on the high level, on paper, it sounds pretty straightforward. On the actual design, as I said earlier, you need to kind of time everything perfectly. You need to make sure everything is organized and orchestrated in a way that data is being forwarded to the right components. So if you actually take a class that's involved with the like more like a circuit design as well as digital design, these classes would talk about how you would orchestrate it across multiple clock cycles. And that's where you appreciate the benevolence, I guess, of having a debugger. So how many people here went through the digital design class at MUIC? Okay, so if it's all of you, I assume you did things on a simulator, right? You never actually like have to put the code in the hardware, like on an FPGA or anything. So this is also a side story again, but if you really need to kind of like put the program your FPGA, okay, you just do the simple adder. So that's not too bad. So if you are taking the OS class, there'll be a point where you need to modify certain part of the program and you don't really know how to debug it, right? This applies to hardware too. We are trying to program the hardware components. And what happens is if you time things wrong, your results will be incorrect. But because it's done in hardware, the only thing you see are LED lights. LED lights again that show as a digit number, like the 8 thing that you see on the screen. This thing on the screen. Have you seen this number, the number on the elevator, right? Have you guys ever look at the number of what floor you're on the elevator? It actually has like different LED. Each of these bar is one LED light. So what you can do is you can program it such that it can show some letter. Those letter become the error code that we are expecting. Okay, if we see AA, it means something happened here. If we see AB, is another different thing that happened. But that's how you can debug the hardware. It's pretty, and trust me, this is annoying. So you need to kind of like read, okay, if this LED lights up, this thing goes wrong. If this LED lights up, this thing goes wrong, assuming that you program the LED correctly, right? So So when you have to design accelerators on FPGA, which is a pretty common thing nowadays if you want to squeeze out performance, right? So these are things that you might need to get used to. And it's not too bad once you get used to it. There are tools that allow you to make it simpler. You can do it in simulation first. There's a lot of tools that you can do to simulate your hardware. And then you load it to FPGA and then more things can go wrong, but at least hopefully see with it. So, I hope that was interesting. I hope you see a little bit more, I hope a clearer picture on whatever you learn in digital design, how to translate here. The reason why I don't want you to implement e-simulator in Verilog or like hardware simulator is I don't want you to go through the pain of debugging the hardware, assuming, which I think I assume correctly, that you never really have to do anything on hardware, like a piece of hardware. This is not the right time. I think it's much better to understand how computer works, how it translates from all the way from your program down to the memories. Those are more important as a software programmer or CS major. All right. So, any question about accelerator design before we move on to one of the things that I would like you to at least see in this class? Again, not going to be on the exam, but I think it's interesting for hardware security to come up. Again, not will not be our exam if that's not clear already. All right. So let me ask you the first question. Why should you care about your own security? I know it's a really open-ended question. I just want to get the discussion going. This is like pretty talk slash discussion based lecture. Uh, and this is a pretty silent chat room right now. Yes, that's one major part of it. Like you want to keep your personal data safe, right? My answer is actually even weak, more weak than this. Why shouldn't you, right? How many people, when you develop a software, cares about your user security? Let me be honest here, right? Whenever you finish an assignment, like, do you ever think about security? Nope. Okay, cool. Because oh yeah, thank you that you said yes. But maybe yeah, I think people more like act upon it, right? If you found okay something is not secure, you patch it. One thing I realized is a lot of people will start using this like agile development cycle. So one thing I really want you to keep thinking is like, hey, I know agile is like also involve things like develop the thing fast and patch it whenever you need it and things like that. And please think about the security as one of the major goals that you need to deliver. It's a pretty big debt trap in agile development. I've seen a lot of big companies that at some point have data leaks. It always tanked their stock for a little bit, so they got into a lot of trouble afterwards. So you want to do a startup at some point, please consider security as one of the fundamental features that comes with your program. Don't give people like hackers your users' personal data. Like seriously, make sure you're aware of it, right? This was not is right. back around I think March, there was a lot of like problem with Zoom. It happens that if I recall correctly, Zoom happened to use one of the Facebook API calls that Facebook stopped using because they already patched it to a newer version of that API, which means that the patch fixed some of the security flaw, but Zoom allows it. So you might have seen some news where there was like random hackers jumping into like a Zoom meeting and start to share the screen and play nude video, right? Uh, yeah, it was on the news and it actually impacts like quite a bit of reputation on the company, right? So you don't want to be that guy who say own a startup, try to launch it, you launch it successfully, things start to get traction, and crap happens. I'm not saying it's impossible to fix, but it's annoying to fix. So there are reasons why you want to provide security in software for sure, right? You also might want to think about hardware security, right? So we are not going to talk about security provided by the software, but most of the time this is kind of like developed through a bunch of like number theory, such as RSA encryption. It has many applications like SHA 0123. Typically, this is designed to secure unauthorized data access. These data literally mean bits, the binary, 0 and 1s that have to be protected, and failure can be pretty bad. What's the role of hardware in this? Well, what if I say I'm a hacker and I thought, okay, I'm bad at math, right? I should be honest, I'm pretty bad at algorithm, right? That's why I do hardware. That's actually when I realized, hey, if I'm doing theory or doing the develop new algorithm, I'm going to fall behind. It's like there's always like a guy like a John Kanat who is like really bright and like I'm not that smart. So that's why I decided to do hardware, right? But the thing is, if you are that kind of person, right, if you want to perform an attack, instead of doing it in software, because I suck at doing software development, I'm gonna attack it from the hardware point of view. Why is this possible? Well, specific architectural optimization can expose some possible vulnerability, right? What does the other role of hardware? If you want to do, say, RSA encryption, you can use Accelerator, Systolic arrays, things that we just learned from the first portion of this class, it's like today's class, to make software encryption faster, right? This is exactly what a lot of company has in mind. We want to be able to do encryption in hardware because doing it in software is a lot of math operation. Let's do this in hardware, it's a lot faster and we have to do it all the time. So let me actually talk about different attacks you can do. Hopefully you find this somewhat interesting. The first common attack is called the side channel attack. The idea is, well, when you have electrical signal going through a wire, right? High school physics. What happens if I have a wire going this way, current going this way? What happened to the magnetic field? If I have current going through my wire this way, I use the right hand rule, right? I have current going this way. It means I will have this wire generate magnetic field around the wire. With me so far? Basically, whenever you have data going through wires, it generates magnetic field. Yes, no, with me so far? And I know a lot of you are already abandoned physics, but then just trust me, when you have electron going that way, right hand rule, magnetic field going around the wires. what can I do is basically I can have another device that listens to that magnetic signal to basically read the signal to try to figure out is that a one or is that a zero. So a super basic example is uh, this is not the magnetic signal, but have you ever realized when you own desktop computer before the fanless design, right? The fanless design. If you have a computer fan, whenever you are computing things, the fan will blow like crazy, right? It will be loud, right? It means that this is a compute intensive phase. You are using a lot of processor. You can then figure out, hey, it's in a loop. Inside the loop, that's not a lot of array accesses. Everything is in the CPU. The CPU heats up. That's when the fan starts blowing. Why can I deduct to that? DRAM typically generate less heat. They come with its own heat sink. Like the cover of DRAM, those are the heat sink for your DRAM. They generate a lot less heat than the CPU. If the CPU's fan start blowing, it means something is doing something in the CPU for sure. It can trigger the beginning of an attack, right? That, hey, you're running something. Let me actually try to read what you're running. You can also, as I said, measure the power and magnetic field that leak out of the device, right? When you are loading or storing data to the cache, if you have a magnetic device that reads the magnetic signal, you can see certain graphs, you can see certain signatures, right? And why do you care about this signature? And oh, okay, let me first ask this question. Why do you see different signatures of each operation when you add, when you multiply, when you do the divide, subtract, and or they consume a different amount of power. It's just a tiny bit different. But if you have a device good enough that you can tell the difference, you can know that hey, you are doing an add followed by a multiply, followed by an add, followed by a multiply, for example, right? You might be able to figure out, hey, you're in a loop in a program. It means you can tap into the data can tap the data and you can measure the timing information. You see the same pattern every 5 seconds. What does it mean? There's likely a loop. It's a pretty big loop because you spend 5 seconds on that loop, right? Any questions so far? So one of the attacks that I have read papers on when it involves side channel attacks are let me ask you this. How many people here got sick of like paying electric bill? Yes, no, both. Electric bill can be costly, right? So that can some bad folks are basically trying to figure out at the meter. If you have a meter that transmit digital signal, basically it's not this analog meter that the people from the electrical company comes and read the meter, but instead you have a digital meter where it sends how much electricity you've been using, right? One thing you can do is put in a device that reads the output and then hijack it and send a different reading. This is basically stealing power. Okay, so they exist, and it's actually one of the potentially problem that you have to kind of tackle if you own the electric company. If you can figure out, hey, this is a loop, you know the timing information. You can do a timing attack. A timing attack is basically, you know the ALU will take a different amount of time to perform, right? Add might take 3 cycles, multiply take 5 cycles. Data access also takes a different amount of time to perform. So if you can read the timing, you know, hey, every 3 milliseconds, oh no, every three like nanosecond, this signal happens. Then every 10 nanoseconds afterward, you see another repeat of the signal. You might be able to deduct that, hey, you're doing an add followed by a multiply. You can use this part of the time to understand when you are running the program and what you are running. Basically, you can figure out the relevant part of the program that you run. Sometimes you might be able to access, you know exactly, hey, the password information is being transmitted from the memory to the CPU. I will then try to read the password. Right? What happened is, even though you try to encrypt the data, you try to encrypt the data inside the memory, at some point, your data in the cache is unencrypted. It means that you are not protected anymore inside the cache, right? You are actually using the raw data. You can access to the key where you connect to a server and you want to hijack the connection, but you need to figure out what's the key. Otherwise, you cannot get any response from the server, right? So you can figure out, hey, what's the key? I would time it such that the key, once it's in the cache, I will go and read it. How is that possible? If you heard about the news called Spectre and Meltdown vulnerability in multiple processor back around 2 years ago. Once you can time it, you can then read the content of your cache. So before we go to that, let's go to one more attack called the cold boot attack. So when you delete a file, instead of actually erasing the file, this will happen. That's the software called the file system. It manages your files, right? It will mark that sector as deleted. The actual data is still there on the hard drive or SSD, right? Anyone want to guess why is this the case? Why is it just marked as deleted instead of actually deleting the data? So let me ask you a different question. Let's say you have a 1 GB file. Let's say you have a 1 GB file. How long? Yes, okay, yeah, you got it. So it's a lot faster, right? If you need to delete 1 GB file, it might take, how long would it take to delete 1 GB file on Windows? Less than 1 second, right? But if you need to transfer 1 GB file, which means I'm writing to a different location, how long does it take? At least a few seconds. At least a few seconds, right? So these operations is way faster. If you have an SSD, the second benefit is you don't have to destroy the SSD cell. Every time you write to the SSD, you're killing it, right? So the fewer time you have to write on the SSD, the better. Which means that, well, if you can figure out how to scan to the hard drive manually, you can still find the data at the right place, right at the same place, right? The same bit pattern. This is actually why you can recover data in some cases where the data doesn't get overwritten. And if you so this is actually a common technique that the police can use to recover the thief data, right? So I got an opportunity to talk to one of the lady coming from like a FBI version of basically she's from Japan, and where she works is basically is the same as the FBI in the US, right? So she actually deal with some of the cases where you have the bad guy having hard drive, and the problem is that we need to figure out, she need to figure out what's the content of the hard drive inside the hard drive, right? So you can do this kind of attack to read the data inside each of the sector that might have gotten deleted, right? So you can see these kind of attack can be a useful thing as well, if it's used legally and lawfully in a good way, right? Now let's talk about the attack on speculation. So what is speculation? So speculation means that we eagerly use the speculated data or addresses. For example, if you do branch prediction, right, you put the new path, one of the prediction in the pipeline. You say, hey, I want to take that branch because I think it's taken branch. I'm gonna keep running that taken path. That is already speculated. It means you're guessing. It means you're guessing. Why is it useful? The same reason as why you have branch prediction. It's faster, right? Basically, you can speculate on branches, speculate on an address. You can speculate even on the data. It's called value prediction, right? So there's an attack called Spectre and Meltdown that target these particular optimizations. And here's the idea. If you look at out of order processor, right, to fetch data out of order, you have load A, load B, store to C, store to D. You can do A and then with the out of order processor, C and D and B are done. Well, basically the order is done this way. A go into the cache, C go into the cache, D go into the cache, then B go into the cache. I'm not talking about the architectural state. This is speculated. It's speculated. So I'll put A, then C, then D, then B. Right? These data can be from different instruction stream. What does it mean? From different threads, right? They can be from different applications. So maybe they're from the OS, right? Maybe they're from the OS. So my question is, well, what if we try to load this data illegally? Because if you speculate on this data, right? So let's say this is where your password is, right? And you have a code. So this is a code that have a branch, true, false. If it's true, you load the password. Right. With me so far, basically you have a code that if it becomes true, you are loading the password into the cache. So at this point, password is in the cache. With me so far. Yes, no. It's just a simple code that wants to load a password, but this line of code is in an if-else statement. What if I tell you this is done through branch prediction, and branch prediction say, yeah, maybe I have to go here. This is branch prediction. But the actual path, the actual thing that you're supposed to do is going this way. It's going this way. Can I ask you what happened to this? Is that still in the cache? Even though you mispredict, is that data still in the cache? Yep. Yes, you're correct. The data is in the cache, which means that the data is not supposed to be in the cache. It's now unprotected, laying in the cache for someone else to see, right? So this is basically what happened. You speculatively execute this thread out of order. This is the meltdown attack. So the paper is in the Unix security. It's one of the top security paper conference, and literally caught a meltdown on Intel stock, which sadly I also owned during the time. I think they dropped like 10%. But you can see why this can be a problem. You are trying to do branch prediction, which is good. It gives you a lot of performance, but this particular branch prediction design caused the password to be read from someone else, right? So basically, once you know this, you can do the timing attack. right? Basically, you know that, hey, I have a block of code through files, load password into the cache. You time it such that you train. So the general idea of this attack is this. You have processor 1 running thread 1 and 2. This is the attacker. This is the, I guess, the victim, which basically run this code. What T2, thread 2 can do is it would train the history table, right? Remember our branch prediction lecture? It's based on the history so that it would train that. It would train the branch predictor so that it thinks that, hey, I should go into this path. That's totally possible. Basically, you can write codes to train your branch predictor logic so that it goes to the taken path. While in reality, this program is supposed to go into the false path. Okay? Once you do that, then you detect, hey, if I know the timing, I'm doing the load right now. I know that if you look at the L2 cache, this is shared. Your password is lying here for everyone else to see. And for everyone else to see. And you just happen to want to look, oops, look this up. Even though it's a cache miss, you already look it up, right? So based on specific implementation of some of the processor, you just happen to be able to access that particular data. And the bad thing of hardware bugs is this. Let's say Intel figure out, hey, I have that bug. What can you do? Can you patch it? So my first answer is this possible to patch? Can I say, hey, I want to change my cache inside your CPU? Give me 3 minutes. I'm going to poke holes on your processor and hopefully patch it. No, right? So literally, you can patch them. You can patch software. It's much harder to patch hardware that you already sold, right? You can say, hey, I want all your CPU back. I'm going to give you a new version of the CPU with no bugs. No one would do that, right? So the next step from the meltdown is the meltdown bug is, well, we can make it more general. This is basically speculative attack. You can speculative, basically, right? We can do speculative execution to load data in the cache earlier, right? And they're good because of performance, right? So here comes speculative attack. First, you as I said, train the branch prediction logic to trick the processor to load the cache line, right? And now the data you want to read is in the cache, and OS can't protect you from it. So the same example that I just described, this is a little bit harder to do compared to that example because you need to still figure out how to read that cache line, right? Any questions so far? Basically, the example that I just said earlier, my bad, I was supposed to describe meltdown. What I just described is like a general version of the meltdown attack. It's called the Spectre attack. It's actually more flexible to attack than the meltdown. Any questions so far? So before we go to the break, let me tell you, okay, if I can do this attack, and this is kind of like the reason why it's really bad for Intel during the time. What can they read if we can do the attack? Everything. The attack allows you to selectively pick what addresses to read from. Your password, your private keys, everything I exposed. So here is the S&P paper from 2019 again, another top security conference. Just describe the Spectre attack. Notice that it's about a year after, and notice that instead of just Intel processor, now everything is affected except for the GPU. Anyone want to take a guess why GPU is not affected? Anyone want to take a guess on why GPU is like Nvidia actually came out and said, "Hey, we're fine." Seriously, like there was a announcement right after this paper. Nvidia came and say, "Hey, our GPU is not possible to attack our GPU through these two attacks." Anyone want to take a guess on why this is the case? So do you remember that we said, "Hey, our attack look at out of order processor"? Is GPU in order or out of order? So let me just ask that question. Assuming they're still here, not tuning out already. Is GPU processor consists of a bunch of in order processor or out of order processor? So actually GPU is in order. You do fetch, decode, execute, memory, write back. You never do it in a different order. So GPU is like a really simple in order processor. It just happened that throughput is really high because you have a bunch of ALU. This is actually one of the big reasons why GPU will suck if you run a single thread program on a GPU. So GPU is in order. In this particular bug, it only happened for out of order processor. So luckily, NVIDIA is like, hey, we don't have this bug. It is as simple as that, right? Fundamentally, because GPU is in order processor, there's no speculative execution. Everything is done speculatively, right? So you don't have the bug. So how to deal with it? Naive solution is to disable speculative execution and make the CPU a lot slower. Or you can flush the cache, right? Making sure that whenever this thing is in the cache and you have branch prediction that I'm wrong, right? When you're in a wrong path, you call this instruction. This is a x86 instruction that flush basically get rid of everything in the cache, right? So this comes with performance overhead. The next thing you can do is called secure on cloud, which is basically you design the hardware assuming that nothing is secure, and we'll discuss this in the basically later in the bit, actually after the break. So impact on this particular attack on the hardware design is because speculation gives a lot of performance out of order and branch prediction is a really, really important concept. That's why you are learning it in the first part of this class, right? It's really important. And Spectre and Meltdown can like disable some of these fancy optimization. So it actually creates this important fact that you just can't protect the data from the software. You need to also protect your data in hardware. So let's do a break, maybe until 120. Is that okay? Basically, we'll be back at 120. And we will talk about this new like security shift, like beyond typical security that we've been talking about and see where the industry is going. All right, so let's do a 5 minutes break. I'm gonna go grab my coffee. Grab yours. Hopefully we go through the discussion here, and hopefully it's fun for you guys. And we will be right back. All right, 120. All right, so let's resume our discussion. Basically, before the break, we talk about some problems, right? Attacks that you can do with hardware. So how do you protect against it, basically beyond like a typical security that you know about in software? What if you need to design a computer? You want to make sure multiple applications can use it because well, that's how you can design a computer that is useful. But you can't trust anything. So open-end discussion. What can happen if you don't know you can trust the OS? Can you run Docker? How many of you use Docker for or any other form of container to run your application? Yes. So one of the good things about Docker is it shares the same kernel and the same OS as the host machine, right? The difference between Docker and VM is VM actually utilize its own virtual, but not virtual OS, but like you have its own OS inside an OS, right? Docker is not the case, right? It's still like you launch it based on the same kind of like kernel setup as the host machine. What if I tell you that I can't? What if I cannot trust the host? It means I can't run any container, right? Is that bad? Yes. It means that somehow I can run a lot of applications. So if you actually cannot trust the OS, the next step, wow, if you still want to run things, right? Well, let's say these days, who knows? Like, can you trust when you run things on Amazon Cloud, on Google, on Microsoft, right? So, what you need to guarantee? Well, assumption, as I said, OS can be vulnerable. So, in a high level, what we have through virtual memory is we have memory protection. What's the problem with this? You thought you can trust the OS. You cannot trust the OS and the OS manage this thing. Manage virtual address into physical address. So you can't trust that anymore. You have no memory protection, right? One other things we can do is, well, we can try to isolate the two different processes, scheduling things at a different time. The problem is OS control the scheduler, right? So if you can't trust the OS, you can't trust this. You can trust. You see the problem here. Basically, I can't trust no one. Basically now I can't trust anything. Here comes the hardware, right? The one of the technology is called Intel FGX, right? Where assumption is I can't trust anything in the memory, right? Because the OS can attack through the virtual memory VA to physical address mapping, allowing some application to access your data. So the idea in Intel SGX is basically okay. If I can't trust the OS, what does the OS provide you? OS provide virtual to physical mapping, right? So Intel say, hey, okay, if we can trust the OS, we will define our own mapping. Special location of your memory is called enclave page table or EPC. This EPC has nothing to do with any memory region that the OS can touch, right? Basically, this part cannot be accessed by the OS, cannot be accessed by the untrusted application, right? The OS only provide the mapping between virtual to physical to this area, but the CPU through Intel FGX perform the authentication So basically, you have this linear section in the memory saying, "Hey, no one can touch it. OS cannot access it. OS cannot read it. OS can only provide if this is the virtual address. That's where you go. I don't know what the data is, but that's where you go. You only see the address. You don't see what the data looks like. With me so far? Basically, you won't let anyone unless you authenticate what application you're running to access those pages. Right? So basically, this is what it looks like. You have this region in the memory, right? DRAM. This is the CPU. This is the OS. Right? CPU runs some of the OS code. This is the EPC. This is typical memory. OS has the mapping to both, so this is the mapping. You can read and write from here. You cannot read and write through here. This is done through the application. Right? So once you have the virtual address, it checks with the OS. OS gives you these particular mapping, so it knows, okay, my data is securely stored here. Physical address, access. Oh, actually not. Physical address, which then access directly through the EPC. OS is not involved except for giving you the physical address. This part is done in hardware because the application cannot touch the physical address, so this is handled by hardware. The CPU say, okay, that's where you go get my data. These bypass using the cache. So if you want to discuss what's the benefit, well, obviously you allow the hardware to provide another encryption layer and protect the data. It's you can store keys or critical code that's protected by the IP right here. Downside, you're not using the cache, which means that the performance would tank, right? That's why you only store important stuff like keys or critical code. And it's linearly managed and mapped, which means you can have things like fragmentation. We are not going to talk about the fragmentation problem in detail, but basically it's when you allocate some of the pages and it doesn't use the entire block, so you lose some of the space that you're supposed to be able to access. Any questions so far? So this is what one of the possible solution from Intel. If you look at the Apple security chip, which is I think introduced along with the A7 processor, and it's been there, including the M1 processor that was announced last Tuesday, right? Uh, Apple come with the design and said this, hey, our idea is, well, we want to, instead of using the CPU like an Intel solution, right? We want an isolated piece of processor that store the touch ID data, face ID data, and all the keys, right? But similar to the Intel SGX, is share the same memory. You actually use the hardware to protect this region. So you have the CPU. This is security chip. This is the application, right? So when you run an app, say on an iPhone, sometimes, well, most of the time you want to access the data, right? It goes through the CPU like normal. So this is the shared memory, this DRAM, data access. But sometimes your application say, hey, I want to check the touch ID info. Or you want to check the face ID, right? This is common. Let's say you go to a banking app, it asks for you for the fingerprint or the face ID. Okay, sorry, my phone still have the touch ID. These days I know it's face ID, but whatever. Basically, it is a way to authenticate that that's you using the phone. Instead of sending the data through the CPU, you don't do that. The call to be done through an API. The API call this data request through this security ship. Security ship would then access a special location in your DRAM, which is secure, right? So this way you can access your protected data and it's totally isolated from the CPU access from the OS, right? It's coming directly from the app. Any questions so far? So I already draw it. So basically see earlier slide for the example. And basically this is what I'm guessing. Some of these are publicly available. Some of these are not really telling me what they did. Like I was not able to find more information about this technology. But this is some of these are my like guess on this is what they how they handle it. Some of these are actual information I found on description from Apple. So if you read the description, you can kind of like guess what that they actually doing, right? So I know they have a separate chip. I know the separate chip access separate region in DRAM, and the application basically whenever this data are request, it's done through the separate chip. So I think this is basically how they did it. Uh, in all, basically what you want is isolation. Like you want to isolate the key and password information from other data and don't utilize the shared hardware resource. The key downside is going to be slow. Right? So all the work that we are doing these days as the architect, we are trying to figure out how to recover this performance loss. Whenever you talk about hardware security, there are typically two branches of work. First one, how can I invent new attacks? That's obvious that you want to be able to invent new attacks so you can protect against future threats. Then you figure out, okay, this way to protect the current attack stuck in terms of performance, how can I make it faster? So that's generally the key. And if you are any of you here interested in this, I have a collaboration with my old research group back in CMU. Now they're at ETS Zurich. So if you're interested in this, definitely let me know. This is one of the active area that I kind of like been touching a little bit and looking around. We have not actually dived into this aspect yet because we ended up doing container related things for now, right? Because we figure out, okay, even have a container is slow, so let's make that fast first before we use some of the techniques for security. So if you're interested for whatever reason, it could be for internship, for your senior project, or anything, let me know. And there are different types of isolation, right? When you say isolation, there's performance isolation. We already talked about this during the multiprocessor slides when we have the shared structure. Right now, we want to actually be able to provide data isolation, data that we're not supposed to allow anyone to access, right? Still can have high utilization for that. All right, so a few more lectures. Sorry, it's a lot of me monologuing for today and probably until the end of this semester. When you talk about encryption, the other things you can do is you can port like all these software encryption techniques, do that faster in the hardware. Basically, right now, if you have to do it in the software, it can be slow, right? These algorithms are pretty standard. If you look at AES encryption, they follow certain specific operation. What does it mean? Maxwell with systolic arrays and accelerator design. So the idea is, well, why can't we hand over this part of the algorithm Do that in the microarchitecture and come up with a new instruction. Right? Why is this a good idea? It's simple and it's fast. So Intel actually come up with the AES instruction set for x86. ARM also has their own implementation of AES. Why do we need this? AES encryption is super common and they are good. So as a proposal back in 2008, where you have an IFA support, a new instruction that would allow you to encrypt things in hardware. Initially, this is for performance, and this is still another active area of research topic. I don't personally work on this, so if you would like to check it out, you can let me know. I might be able to get you connected to people who work on this area. That's it for the class today. Any questions that you might have or you're curious about that I can answer?